page 416, section 7.2, exponential functions. All right, we start off on 416 with just a reminder of what an exponential function is. They tell me in general, an exponential function is a function in the form of f of x equals a to the x, where a is a positive constant. Now, they didn't specify for n. N could be several different things. It could be a positive integer, it could be 0, it could be a rational number. So we have all different types of scenarios for our exponent, but a has to be a positive constant. The keys that we studied last year when we studied exponential functions was we said if you're graphing y equals a to the x where a is a number greater than 1, that entire function is going to be increasing. If you're graphing y equals a to the x where a is a number between 0 and 1, that entire function is going to be decreasing. But both of them had two landmarks that we just kind of lived off of. That was the fact that each of them would have a y-intercept at 0, 1, because if you think about it, if you put 0 in the place of x, other than 0, anything to the 0 is going to be 1. So since a has to be a causative constant, we're not going to run into 0 to the 0. So that's why we could count on having a y-intercept of 0, 1. The only exception to that is when we start shifting and reflecting and doing that kind of stuff to it. But for the base graph, that would be a landmark. The other landmark that we had was that there would be a horizontal asymptote at y equals 0 on the x-axis. And we understand a little better now why that's the case if we think about the limits associated with this. So they give me some limit laws associated with the exponential functions on page 419. And they suggest that we memorize these, but honestly, we could use common sense for these. When I'm working with a is greater than 1, if you take the limit as x approaches infinity of that function, you're literally looking at, as x goes off to infinity, what is my y value doing? And you'll notice it's going to infinity. So that makes sense. They also say what's the limit as x approaches negative infinity of that function. So if I'm looking at as x goes to negative infinity, notice my y value is approaching 0. So if I know what the graph looks like, which I should from last year and from this year, if I know what that graph looks like, then I can come up with those two limits without needing to memorize them. Similarly, over here, when a is a number between 0 and 1, if I'm taking the limit as x approaches infinity, then I'm looking at this graph saying, okay, as I go to infinity, what's my y value approaching? It's approaching 0. Or if I'm taking the limit as x approaches negative infinity, then I can come over here and say, okay, as x is going to negative infinity, what's my y value doing? It's going to positive infinity. So you can memorize those 4 limit laws that they give you in the textbook, or you can just look at the graph and they make sense. That leads us to our horizontal asymptote, because remember we learned back in section 4.4, if you take the limit as x approaches a positive or a negative infinity for a function and you actually get a numerical answer for that limit, then that value will be equal to y as a horizontal asymptote. So over here for the function where it's increasing because a is greater than 1, when you take the limit as x approaches negative infinity, you get an answer of 0, so that causes the horizontal asymptote for that function. Whereas when you're looking at the decreasing function when a is between 0 and 1, if you take the limit as x approaches a positive infinity for that function, you get 0, and that causes its horizontal asymptote. So we can see why that each of those landmarks is in place and why we can count on them to be there. All right, so one other thing that they review for us about exponential functions on the bottom of page 418 is they remind me of my laws of exponents. That's basically like when your bases are the same and you're multiplying, you add your exponents. When your bases are the same and you're dividing, you subtract. When you have power raised to a power, you multiply. If you have a quantity raised to a power, you can break it apart, and each of those pieces can be raised to the power. So again, those are listed on the bottom of 418, but I know you've been using those for quite a few years. All right, so look at example number 1. For example number 1, they ask us to evaluate the limit as x approaches infinity of 2 to the negative x minus 1. So let's work this 2 different ways. Let's work it out algebraically using limit laws, and let's work it out graphically and see we would get the same answer either way. Remember, AP loves that multiple representation of information. So let's start with algebraically. If I have 2 to the negative x, now last year in pre-cal, that is how they wrote in our textbook anyway, that was how they wrote this decreasing function over here. They wrote the increasing one as a to the positive x, and they wrote the decreasing one as a to the negative x. They're doing the same thing here, because when they say 2 to the negative x, that'd be like a to the negative x. That's the same thing as 1 over 2 to the positive x, right? And so if I say a to the negative x, or if I say a is a number between 0 and 1 when it's raised to the positive x, it's the same thing. I could write this as 1/2 to the x, or I could write it as 2 to the negative x. Same idea. Whichever one clicks for you is fine. So in any case, I've just rewritten that so that it fits the way that our formula is written in our calculus book. So I have the limit of an exponential and a constant. I'm going to work with those separately. So I'm going to break that into two separate limits. I'm going to work with the limit of the exponential first and the limit of the constant second. Okay, so for this exponential, we've already said that that matches with this decreasing pattern up here. And if I'm taking the limit as x approaches infinity on that decreasing pattern, notice that our limit is 0. So I can look at this, and by those limit laws, I can know that first limit is 0. And then, of course, the limit of a constant is always that constant. And so I could say 0 minus 1 is -1. Look at it graphically. If I'm trying to graph 1/2 to the x, that's going to be the decreasing function that has a y-intercept at 0 and has a horizontal asymptote at the x-axis. So there's that same graph we had up here a second ago. There's my decreasing function. Then I have that -1 tacked on to the end. That 1 could be moved to the other side, right? It's not attached to the x, so I could move it to the other side and subtract it from the y. So is it horizontal shift or vertical shift? Vertical, right. And it's a vertical shift of what? -1. So I'm going to shift it down 1 unit, or a vertical shift of -1. So I could take that x-intercept and move it down 1, and take my asymptote and move it down 1. So that green graph is my shifted graph. And that's the one that I wanted to know the limit as x approaches infinity. So if I look at this and say, what's it doing as x goes to infinity, you can see that it's approaching -1. So whether you had worked it out graphically or algebraically, you'd get that same limit either way. Now, over on page 420, they talk about applications of exponential functions. The exponential function occurs frequently in mathematical models of nature and society, like we've done population growth already this year. Back in section 3.4, they remind us that we were looking at like populations of bacteria and that type of thing. So last year and this year we have done tons of regressions on our calculator, but it's been a little while since perhaps we've done an exponential regression. So let me just go through the example on 420 for you just to review it and make sure that it's fresh in our mind. So on page 420, it says Table 1 shows the data for the population of the world in the 20th century. And so I could use that table there on 420 and load it into my calculator. So I'm going to go to Statistics and go to Edit and enter that information in List 1 and List 2. All right, then to get my calculator to plot what I've just put in the statistics, remember I go to second y equals, which is stat plot. I'm going to turn that first plot on. I'm going to choose a scatter plot from the list of graphs to choose from and tell it to use List 1 and List 2 and whatever little markers that you want to use. So I can get my calculator to set the window for me rather than me having to set the window by hand. If I'll go to Zoom 9, which is Zoom Stat, it takes that data that I put in the statistics and sets the window for me. And so it has generated this graph of those ordered pairs, and you'll see that graph looks just like the one that's there in the textbook or one that we could generate by hand. So looking at that, we can see this is definitely not linear. I might be tempted to think that it might be a quadratic if they didn't tell me that this was population growth, or if they didn't tell me that whatever information I might be working with in the future would be exponential. So I'm going to go through, remember on our calculator we have tons of different regressions to choose from. We've done linear, we've done trigonometric, we've done quadratic. So for this one, since this is that shape that we've been looking at today for our exponential, we would choose our exponential regression. If you want your calculator to auto-load the equation for you, then remember before you hit enter, go ahead and put in your y1 so that it puts that equation in y1 for you. And so when I hit enter, it gives me the equation. Now notice this first number here is in scientific notation, so be careful of that. That's 8.306312 times 10 to the negative 9, so we got to move our decimal. But that would be our A value and that would be our B value if we were writing out the equation. And so you can see that's a pretty good fit. So that's a good model. What's the purpose of doing that? Well, the population was only gathered every 10 years. What if I wanted to, like they gathered it in 1900 and in 1910, what if I wanted to know the population in 1913? They didn't take it that year, but this would give me a way to have a good idea of what it might have been. It's also used a great deal for predictions. If you do a population study, you need to make sure that you have housing and you have transportation and you have jobs and all of that based on where your city's projected population might be, or that population is going to go somewhere else if you can't provide the things that they need. So lots of ramifications of that type of an application. So we've done a lot of those in the past. I just wanted to review back through that with you as we talk about applications of exponential functions. All right, when we talk about the derivative for an exponential function, over on page 422, we want to look specifically at the natural exponential function. Remember the natural base e? E by definition is 2.718281828. So it kind of looks like it repeats, but if you keep going, it does then deviate from that. So it genuinely is irrational, meaning that it's non-repeating and non-terminating. So it's kind of like pi. It's called the natural exponential function because it shows up so often in nature, and because it is such a precise number, we wanted a symbol to represent that because we need to use it so often. So just like we assigned pi, we assigned e. Where it actually comes from, if you're interested in its definition, e is the number such that if you take the limit of e to the h minus 1 over h as h approaches smaller and smaller and smaller values approaching 0, then you'll get an answer of 1. So that's its definition of the number e. So when I'm looking at the derivative of an exponential function, we'll get the derivative of a to the x a little later, but the derivative of e to the x has the unique quality that it is its own derivative. The derivative of e to the x is e to the x. They tell me here in the textbook, geometrically, of all of the possible exponential functions, y equals a to the x, the function e to the x is the one whose tangent line at 0, 1 has a slope, the derivative of the function of 0, that is exactly 1. So thus the exponential function f of x equals e to the x has the property that it is its own derivative. The geometric significance of this is that the slope of a tangent line to the curve y equals e to the x at any point is just equal to the y-coordinate of that point. So that's important, that last statement. It's the last sentence right above example 2 on page 422. It says the significance of this fact is that the slope of a tangent line to the curve y equals e to the x at any point will just be equal to its y-coordinate at that point. So AP loves to play with the exponential function because it has extra traits like that it can utilize. So we see that more often maybe than other graphs on the AP exam. Sometimes, not always. Kind of hard to predict, but. All right. So example number 2. They ask us to find the derivative of y equals e to the tangent of x. Now, we've said that the derivative of e to the x is e to the x. Let's apply chain rule to that. If you don't have just plain e to the x, if you have e to some other quantity, then we could call that quantity u. And so when I do chain rule, the derivative of e to the u would just be e to the u times the derivative of u in terms of x. So derivative of the outside times derivative of the inside. So if we come down here and we look at e to the tangent x, we can say the derivative of e to the tangent x is going to be, let's let tangent x be equal to u. So what would the derivative of tangent be? Ooh, it's been a long time, right? So yeah, the derivative of tangent is going to be secant squared. And I'm still in that differential mode with our integrals. This should say du dx, not just plain du. All right, so if u is tangent and the derivative of u in terms of x is secant squared, then we can come up and use our formula. So our formula says that we'll have e to the u times the derivative of u. E to the u times the derivative of u. So u was tangent and the derivative was secant squared. And that's my whole answer. That's all that I can do with it. Can't simplify that in any way. All right, look at the next one. Example number 3, we have a product. Remember product rule? First times derivative of second plus second times derivative of first, right? So I have two quantities here. Here's first and here's second. All right, so if we start off with a product rule, we're going to do first times derivative of second. What would the derivative of sine be? Cosine, right. And we've got sine of a quantity, right? Sine 5x. So the derivative of sine 5x would be cosine 5x times 5, right, because I have to do the derivative of that quantity as well. So here's first times derivative of second. So we did cosine 5x times the derivative of the 5x. There's our chain rule again. All right, now we need plus second times derivative of first. So let's think about the derivative of e to the negative 4x. What would that be?
Negative 4 e to the negative 4 of x.
Yes. It's going to be negative 4 e to the negative 4x. So we've got our second, and then here's the derivative of the first. It's the derivative of the outside times the derivative of the inside. It's e to the u times the derivative of u in terms of x. So the derivative of negative 4x was negative 4. A little bit of simplifying that we can do here. We can go through, notice that our first term has an e to the negative 4x and our last term has an e to the negative 4x. So we could take out that common factor. It's not mandatory. It's kind of the idea of if you have x times x plus 1, is it more simplified to leave it that way or to distribute? It kind of depends on what we're working with. And so that's kind of the argument here. Am I better to factor out that common factor or to leave it distributed through? Either way, it's really more of an issue of trying to match the answer that we're given on the multiple choice. All right, so everything that we learned earlier about the a to the x function when a was a number greater than 1 will apply to e to the x, right? Because remember, e to the x is just 2.718. So if I know that y equals a to the x where a is greater than 1 is an increasing function with a y-intercept at 1 and a horizontal asymptote at 0. All that's going to be true about e to the x. Our limit laws are still going to hold true as well. The limit approaching infinity will be infinity, and the limit approaching negative infinity will be 0. And again, I could just look at the graph and get that. But all those things that we already saw about a to the x when a is greater than 1 will apply to e to the x. All right, so let's look at a couple of limits with e to the x. For example 6, they ask us, find the limit as x approaches infinity of e to the 2x over e to the 2x plus 1. Remember when we were taking limits approaching infinity and they had us divide everything by the highest power of x in the denominator, and then that made the limit fall together? We're going to do something similar here. We're going to divide everything by the highest power of e in the denominator. So in the denominator, I have e to the 2x. So if I take and divide everything by e to the 2x, e to the 2x divided by e to the 2x is 1. E to the 2x divided by e to the 2x is 1. And then 1 divided by e to the 2x. All right, what's the limit of any constant? That constant. So I'm okay with this guy. The limit of 1 is going to be 1. The limit of 1 is going to be 1. But this is really where I need to focus. The limit of 1 divided by e to the 2x. That's where I kind of get stuck. So there are two ways that I can work that out. I can work it out using logic and common sense, or I actually can come down here and take that limit algebraically. So let's do it both ways. Let's start with just kind of some common sense, right? If we're looking at the limit as x approaches infinity, if I come over here and I say 2 times infinity, now of course we're not actually saying you can multiply 2 times infinity. We're thinking of infinity as a quantity that gets infinitely larger without bound, okay? So when we write 2 times infinity, we're saying double a value getting infinitely larger without bound. So what's that going to be? Infinity. Yeah, a value getting infinitely larger without bound, infinity, all right? If I take e, which is 2.718. So let's just round it off. Let's say it was 3, okay? If I take 3 and I raise it to infinity, basically that's like 3 times 3 times 3 times 3 times 3 times 3. What's that going to? Infinity, right, something getting infinitely larger without bound. So if my numerator is staying the same and my denominator is getting infinitely larger without bound, what is that overall fraction going to do? Go to 0, right. And so that would be a logical way that I could figure out that that limit is 0. And so then I can come over here and say 1 divided by 1 is 1. If you would rather an algebraic way of figuring out that one little piece, again, it's this little guy that's causing us trouble. So let's come down here and let's think about that limit algebraically. I could go through and first off I could rewrite e to the 2x as e to the negative 2x. I have properties for e to the x, not e to the negative 2x. So let's do some substitution. I'm going to replace negative 2x with u. So over here I'll have the limit of e to the u. Well, I can't replace this x with a u and not replace this x with a u. So I'm going to need to redefine what I'm taking the limit approaching. So if u is equal to negative 2x, as x is approaching infinity, I need to figure out what u is approaching. So if I put infinity right here, what is negative 2 times something getting larger without bound? Negative infinity, right. Something getting larger without bound, but going in a negative direction. So we could say then that u would be approaching negative infinity. So if I'm looking at the limit of e to the u as u approaches negative infinity, that is a perfect match for this limit law up here. That limit would be 0, and again, that's how we could find this little piece right here. So logic or algebra, whichever makes more sense to you, you're welcome to utilize. All right, so we've talked about derivatives. Let's think about integrals. If the derivative of e to the x is e to the x, what's the integration of e to the x? E to the x, right. And if it's indefinite, then we'll have our arbitrary constant plus c. And so that's the formula that they give us over on page 425. Integration of e to the x dx is equal to e to the x plus c. All right, so look at example 8. I still have issues when I have a product because I don't have a product rule for integration, right? So I'm going to need to use some u substitution. So what do you want to try? Because remember, this is just trial and error. What do you want to try?
X squared? Yeah.
Okay, I could try letting u be equal to x squared. What are my other choices? All right, let u be equal to x cubed. My problem is the product, right? I also have an issue with I don't know how to integrate e to a quantity. We've said that you can do this by trial and error. Just try a couple of different ones and see what works. But if I'll think about it a little bit, I save myself some trials, right? Because they said try to choose a u that has a derivative also in the equation. So if I choose u to be x cubed, the derivative of that would be 3x squared, and the differential would be 3x squared dx. I've got an x squared dx sitting right there. So I could do it a couple of different ways to find the one that works, but that might save me a little bit of time if I kind of think that through first. So if u is equal to x cubed, then the derivative of that would be 3x squared, and so the differential du would be 3x squared dx. I have x squared dx, so how do I get rid of the 3? Divide it out, right. So I'm going to have 1/3 du is equal to x squared dx. So we can come up here and replace the x squared dx with the 1/3 du, and then this guy is going to be e to the u. So integration of e to the u would be e to the u, and we've got our constant of 1/3 out in front, and then we just need to back substitute and put our x cubed back in. All right, example 9. Find the area under the curve. It never goes away, right? Find the area under the curve y equals e to the negative 3x from 0 to 1. Okay, so if I've got e to the negative 3x, that's the same thing as 1 over e to the positive 3x. So that's going to be one of those decreasing functions. And they asked me to find the area between 0 and 1. So we're going to start right here at 0 and we're going to stop at 1. So if I'm doing area, if I do top minus bottom, that's just going to be e to the negative 3x minus 0. And so we're going to have the integration from 0 to 1 of e to the negative 3x. All right, so what do you want to use for u?
Negative 3x.
All right, so let's try u is equal to negative 3x. The derivative of that then would be negative 3. So the differential du would be negative 3 dx. I just have a dx. So I had to get rid of the negative 3. So I divided it out. So we can say then that dx is negative 1/3 du. And then negative 3x was u. So that would just be e to the u. Now, I didn't put values on here. I'm still seeing some of you, when you use your u substitution, you're having u's here, but you're using 0 and 1, which are x values here. You can't do that. You either have to identify this as x equals 1, x equals 0, or you have to switch them out for u values. You can't have 0 and 1 here without any other identification, or they're assumed to be u values. So be careful of that. So I'm going to switch my x values to u values. So when x is equal to 1, if I bring that up here, that'd be negative 3 times 1, which is negative 3. And when x is equal to 0, negative 3 times 0 would be 0. Now, notice my lower value is on top and my larger value is on bottom. If that bothers you, you can switch it, but you have to put a negative out in front when you reverse a and b. You can also integrate with them as they are. That's perfectly fine. So we could go through then and say the integration of e to the u is e to the u. And then we could plug in our negative 3 and our 0. What's e to the 0? 1. So that's about the only simplification we could do here. Minus the negative is going to be plus. 1/3 times 1 is going to give us plus 1/3. And again, you may see them take out a common factor of 1/3 and write it in the factored form, or write it in the distributed form. Either one. Really just a matter of matching the answers. All right, because the textbook knows that we are getting close to the AP exam, they're going to start throwing some fabulous review examples in. So as you're going back through and studying this section, pay particular attention to example 5 and example 7. Example 5 asks you to find the absolute maximum of a function. Remember critical numbers, first derivative test, absolute maximums and minimums? Been a while, right? Great example there in number 5. And then example 7, use the first and second derivatives together with asymptotes to sketch the graph. Remember 4.5 and 4.6 where we went through all those steps? So graphing with the first and second derivative test, great example there as well. All right, so here is our homework for tonight on pages 426 and 427.